We were just talking about the Beta-Bernoulli model, a model where we take some Bernoulli distributed random variables with a beta prior on the parameter, the probability of getting heads, if we interpret these as coin flips, and we computed the posterior distribution. It was pretty easy. We just multiplied together the likelihood and the prior, and we found that it gave us a beta distribution, or it was proportional to a beta, so that the posterior is this beta distribution. And we computed just using the properties of a beta distribution, using the beautiful fact that this was conjugate. We were able to get this in closed form and just use these very simple properties of a beta to get the same properties for the posterior. So now I'd like to think a little bit, make a few more connections here. And if you think back to when we were computing maximum likelihood estimates, or if you know about maximum likelihood estimates, then these random variables x, these Bernoulli random variables, they're just random variables on a finite set on 0 and 1, right? So when we computed the MLE for the PMF of a random variable on a finite set, we found that the MLE was just the empirical distribution. Empirical distribution. Well, the MLE for the parameters, maybe I shouldn't say it that way. It's since this theta is just the probability of getting ones, of getting a 1, then this is the empirical probability of getting 1. So this is just n1, the number of ones that we observe, divided by the total number of flips. So before we were considering a vector of probabilities, and that vector then would be n1, or it would be n0 over n, n1 over n. This would be the empirical distribution. So that's the MLE, and we can also immediately get the map. Because what's the map? Well, it's the maximum a posteriori estimate, and we have the posterior distribution. We've got it right here in our hands. This is the posterior distribution, and the maximum a posteriori, maximum, is the mode. That's the definition of the mode. So this is the map. We've got it. We've got it right there. A plus n1 minus 1 divided by a plus b, maybe a little more space there, a plus b plus n minus 2. So that's just our map. We just got it. And so I'd like to do a little calculation here. It turns out that both the posterior mean and the map are convex combinations of the MLE and the prior mean, or rather, well, so this is a convex combination of the MLE and the prior mean. This is a convex combination of the prior mode and the MLE. But let's just do it for the case of the mean. So this posterior mean, this thing, we want to write it as alpha, so I'll just put it here. We want to get this in the form alpha times, let's see, what's the prior mean was, our prior was this thing. Maybe I should have put theta here. This is our prior. Yeah, that was a little confusing. You could think about, yeah, I shouldn't have put x here. That was since we were using x for something else. That I should have put theta. So our prior mean was this a over a plus b. Let me change that. That's annoying me. So this should have been, I should have put, I was thinking just abstractly about a random variable, but I should have put theta here. Since theta was, right, we were assuming that theta did have this distribution. So that was a bit strange for me to do that. Okay, but this was our prior mean, so we want to get this as a convex combination of that and the MLE, which is n1 over n. And alpha here is going to be, we want this to be in the interval from 0 to 1. So that's what we want. And we can just, let's just divide, so we can just write a, what do we want to write? A over a plus b over a plus b plus n, right? Those cancel, and gives us the first part. And then we have n1 over n times n over a plus b plus n. That cancels and gives us the second part. And so this will be in this form as long as these two numbers add up to 1. And if we add them together, indeed they do. So this shows that this is a convex combination. So that's always nice. It's always nice to be able to interpret this in this way, because as the data, as n goes to infinity, the prior mean, this was the prior mean, the influence of this is going to 0. And the influence of this as n goes to infinity is going, this term is going to 1, this factor is going to 1. So the MLE is dominating. So that means that the posterior mean is converging to the same thing that the MLE is converging to. And that's always nice. And also when n is 0, right, you can see when n is 0, this drops out, and we revert back to the prior mean. So when we have no data, we just use the prior mean. And that's a nice fact. Okay, let's compute now the predictive distribution. Oh, that's a nice color. Predictive distribution. That's the other thing that's often very nice to have your hands on. And what's that? That's just the probability that x, now x is my, x is the thing that I wanted it to be, this thing. And and maybe I should have said here, if it wasn't clear, these are independent. And this one's also independent. They're conditionally independent given theta. Right. This is also conditionally independent of everything given theta. So the predictive distribution is the probability, well, I could write it. Often we write it this way, so I'll write it. Well, I'll do it this way first. Probability that x equals 1 given our data, right? The probability of, so this would be the probability if we flip after seeing, heads and tails a bunch of times, what's the probability of getting a heads? So this is our, sometimes we say posterior predictive. And this, well, what do we need to do? We need to introduce our parameter theta. So we'll integrate over theta. So this is the probability of x equals 1 given the data and theta times the density on theta given the data. And this part just becomes, this, since x is conditionally independent of the data given theta, this becomes probability x equals 1 given theta times the posterior. And this is integrating with respect to theta from 0 to 1. So this becomes, so we can use the fact that the posterior distribution, we have an expression for that. It's just this beta distribution, right? So we can plug that in. So we get, first, this part, this is the probability of getting a 1, and that's of course just theta, right? For a Bernoulli random variable, that's the probability of getting heads. And the posterior is this beta distribution, the density of a beta, with parameters a plus n1 and b plus n0, integrating with respect to theta. And what is this? This should be very familiar. Well, it's just the expected value of this distribution, right? That's it. So this is nice. This is a nice fact. This is looking beautiful. This is the expected value of theta given the data. This is just the expected value of the posterior distribution. And we know what that is. The expected value of the posterior is this thing, a plus n1 over a plus b plus n. A plus n1 over a plus b plus n. So we can compute the predictive distribution in closed form. So this says that the probability of getting heads after seeing all this data is just this. So it's sort of, you could think of it as sort of, well, I guess we did. We were thinking about it in this way. We were thinking about it this, right? This is the same thing that we just wrote as the convex combination. The probability of getting heads after seeing all this data, it's a convex combination of the MLE. You can think about it as sort of like the MLE modified by our prior mean. So modified by, for example, if this was, so a special example of this, so I should have maybe pointed this out before. If we took a and b equal to 1, remember that was when it was a uniform distribution. And if we did that, if we took a and b equal to 1, then what would happen? Well, let's see. Is that what I want to say? A and b equal to 1. No, I guess that's not exactly what I want to say. No. Okay, no, forget that. So, but anyway, you can think of it in this way. What the predictive distribution is sort of like this, the MLE modified by our prior, or the other way around, the prior modified by our observations. We sort of update the prior with our observations. So, for example, if you saw a ton of heads, right, or every single one was heads, right, then you're going to move from your prior towards something closer to 1. So you're going to expect heads in the future. You're going to expect there to be a higher probability of heads in the future if everything you've seen in the past was heads, or if you saw a bunch of heads in the past. All right, so that's it. We just computed the we did this very nice. It was a very simple analysis for the Beta-Bernoulli model, and we saw that it was the beta was a conjugate prior. We got the posterior. It was a beta. We saw these quantities for the posterior. We saw that the posterior mean was a convex combination, and we got the predictive distribution.